Good. So thank you for your patience. I hope the screen mirroring continues to work. And thank you so much to Chong-Hei for giving me the opportunity to talk here and for the invitation to come to KIAS. So the story I want to tell you really goes back a very long way in human history and in our human endeavor to try and understand the motion of the bright objects we see in the night sky. And that led to ideas in the 1700s to try and model and predict where the planets were going in the sky. And of course, we now know that the orbits of planets, or even protoplanets like Pluto, travel along very beautiful shapes that are called ellipses. And this was formulated by Kepler. Now, I hope this works. Yes. In the 1700s, he wrote down 3 laws, and his first law was that the orbit of every planet follows an ellipse with the sun at one of its 2 foci. And because the sun is so massive, the ellipse is effectively a circle, really, but I've drawn it in a distorted way here so you can see something about what he intended. And the planet, as you see with that rough arrow, is following that shape in the sky, in the elliptic plane that goes through the equator of the sun. So this idea and many of the other efforts that people were making around that time led to an incredible amount of interest from mathematical people, including people like Newton. And there's a lovely article by Arnold and a collaborator in the notices of the AMS. You can go and look up. I can give you references another time, where Arnold explains how Newton developed an entirely new topological idea around this time in connection with the study of planetary orbits. So we know what the equation of an ellipse is. It's given by that polynomial equation. For an ellipse, A is not necessarily equal to B. And so if we take a center of the ellipse and draw to the position of the planet on the ellipse and give it the coordinate x and y with respect to that origin, then those coordinates satisfy a polynomial equation. But now think about what this means for other properties that the planet uses or displays in its orbit. And if we now think about the arc length that is traveled by the trajectory of that planet, or the area that's swept out by the ray to the ellipse, then they are also functions of the position of that planet on the ellipse. So they are functions of x and y. So Newton asked a very simple question. This is explained in his Principia Mathematica, if you ever want to go and look at it. So Newton asked in about 1687 whether the arc length and the area swept out by that planet are also solutions of polynomial equations. And after asking that question, he himself gave the answer in, I think it's Lemma 28 in the Principia, which is written in Latin, if you ever want to go and check it out. The argument he gave, which is explained by Arnold in his notices article, is that as xy moves along the orbit with time, and we return after a year of rotation around the sun to the starting point, then the ray would have swept out the whole area inside the ellipse, or the whole arc length of that orbit. And the planet doesn't stop there. It keeps going. Each time it sweeps out a year around the sun, the area and the arc length will increase again. And then again and again, each time it repeats the orbit. So in fact, at each point on the ellipse, the value of the arc length and the value of the area swept out by it takes an infinite number of values. And what Newton tries to point out is that, therefore, it can't be the solution. These quantities, the area or the arc length, can't be the solution of a polynomial equation in x, y, because a solution of a polynomial can only take on a finite number of values, which is determined by the degree of the polynomial. This is the quasi-topological argument that he gives, which is used by Arnold actually to study the same question in higher dimensions. It's a lovely, lovely exposition, and I recommend it to you. But what all this means is that at the end of that thought experiment, what we see is that the area and the arc length subtended by a planet on such an orbit cannot be solutions of a polynomial equation in the coordinates. Therefore, they are transcendental functions. This sets the scene for the study of functions that go well beyond the solutions of polynomial equations, that is, beyond algebraic functions. And it also led to many, many other developments in mathematics, as you probably all know already. And Euler pointed out a long time ago that you can actually work out how to calculate the arc length if you take the length along a small piece of the orbit, call it ds for the arc length, the change in the arc length, then Pythagoras' theorem tells us how to write down that quantity in terms of the angle of that vector from, say, the vertical. And because x and y satisfy that polynomial equation, we have this formula for ds squared in terms of d theta squared, the small change in the angle. And so we can write down the arc length, but you can also do it for area, arc length in terms of this integral from, say, 0 at the vertical to the angle theta, given by this square root of 1 minus something times sine squared. That was the beginning of the story. Around that time, the history is fascinating. I think there are multiple big names that you would know involved in this story. Bernoulli, for example, looked at a special case of this integral. He worked out that you can have an addition formula for such quantities. Then Legendre came along later and showed that there were only three types of such integrals. And we usually call them the first kind, the second kind, and the third kind now of what are now called elliptic integrals. But the elliptic here is only a kind of a memory of the ellipse that the planet was traveling on. It's not actually associated with an ellipse anymore. And Weierstrass came along later in the 1800s and decided that it was better to look at this integral in an algebraic way. In fact, you can rewrite the sine squared and rewrite this square root function inside the first integral as a quartic in a new variable. But Weierstrass came along and said, no, it's better to look at it as a cubic. You can easily map between them, the quartic and the cubic terms, and developed a whole analytic theory around it. But along the way, there was huge amounts done by Gauss, who never published it, apparently. And then Abel came along and showed that you can invert these integrals and that the inverse function is well-defined and is what we now call elliptic functions. And Gauss complained that Abel stole his work. But since Gauss never published it, it wasn't clear exactly what happened. So we now end up with functions that are the inverses of these integrals. So here at the end of the slide, we're talking now when you take the inverse of defining w as a function of t. And that's the dynamics that I'm interested in. So this Weierstrass form, which is what's used as a canonical form widely whenever we talk about such motion and such curves. The inverse function, as you know, is this curly p, and it's a function of those two parameters left in the polynomial, the g2 and the g3. But from my point of view, as a person interested in the analytic theory of differential equations, it's also of great interest that these functions, the w as a function of t, satisfy differential equations. So here the dot means d by dt of that function. And by just looking at the derivative of that integral, you can easily deduce the first equation. The first derivative of w squared is that cubic. And then you can differentiate again and get the second order form of the equation at the end. So I want to look at the reverse story. If I'm given a differential equation and I want to understand the global behavior of the solutions of that equation, how can I reproduce this story? Can I go backwards from the differential equation and redevelop and rederive all of the beautiful things that we know about elliptic functions and the associated theory? And this question is an important one, I think, not just because I'm interested in it, but because so many people have found it a fruitful direction. I mean, there are so many things to say about the functions that parameterize such cubic curves that I would be spending the next month trying to give you lectures on it if I were to go through all of it. But let me just point out a couple of things. Newton also classified all real cubic curves in terms of singularities and normal forms. And he defined things through what we now call Puiseux series. Puiseux came along much later, so that we can look at, for example, the solution of that simple example of the cubic, which is here, around, say, x equals 0, and get a power series expansion which converges in a covering space. And this leads also to the beginnings of another aspect of the theory, which we now call monodromy. Monodromy comes from two words, mono for one, and dromy comes from dromos, that's following a path. Dromos is a track in Greek, which is also a very productive way of looking at the solutions of these equations. So why is this of interest? Well, because in the late 1800s, this story of elliptic functions and elliptic curves became a powerful driver for new developments. And Felix Klein, and I'm so happy that people have already given talks about Klein in many ways, actually encapsulated this in his Evanston Colloquium, which he gave in Chicago. And I think Christoph mentioned it earlier. He said, "It is well known that the central problem of the whole of modern mathematics is the study of transcendental functions defined by differential equations." So we just went through an argument that showed that the inverses of those integrals can't be algebraic functions, so they're called transcendental functions. And if you reverse the argument I gave and you started with the differential equation and then deduced information about their solutions from it, that was the way, that was the direction that many people at that time of that era were moving to try and extend the theory that was pointed out by elliptic functions. So around this time, 1893, it was like an explosive moment for this question. There were so many people who looked at this problem. Émile Picard did a lot of fundamental work. There's a beautiful paper of his where he shows how to solve a particular very unusual differential equation in terms of elliptic functions, and it turns out that's a special case of the equations I'm going to show you later. Sofia Kovalevskaya or Sonia Kovalevskaya looked at the problem of the rigid motion of a top rotating around a fixed point, and showed how one might look at the solutions of its equations of motion with ideas that became fundamental for the work of Painlevé a bit later on. And then Richard Fuchs, the son of Lazarus Fuchs, worked on this problem. Gambier, Boutroux, there are many, many, many other people leading all the way to the modern times with the work of Manin, Dubrovin, and all of the Riemann-Hilbert theory that is now known about this context. So not many people know Painlevé, so I thought I'd show you a picture of him from an earlier age. He was instrumental in showing how to classify differential equations with properties that gave you globally defined solutions. He was also Prime Minister of France twice, I think, maybe 3 times. He was Minister of War. I don't know how he got time to do mathematics, really. He was the first person to greet Charles Lindbergh when he flew across the Atlantic. So he was a crucial developer of the theory that led to new functions that solve differential equations. These new functions extend the theory of elliptic functions. And this discovery led to him and others around the time to 6 classes of nonlinear differential equations, which are now called the Painlevé equations. These are all second-order differential equations for W as a function of t. They have parameters in them denoted by the Greek letters. When the parameters take special values, they are known to have special solutions. So for example, in the second example, when alpha is 0, you can see that W being identically 0 is a solution. And so on. But when they don't take those special values, when those parameters don't take their special values, then the solutions are known to be higher transcendental functions. They are new in the sense that they are field extensions of the solutions of earlier known differential equations. People like Malgrange and Umemura in Japan and others have shown that kind of result. But what I want to do is to try and give you a glimpse of how we can get the information, global information, about the dynamics of the solutions when we know almost nothing about them. And there are still questions that remain open, and I want to show you something, a trajectory through this field, which is a more geometric idea, geometric development of ideas that lead to that global information, or at least some parts of that global information. So the crucial question here is, what are their global behaviors, and how can we deduce them? There's been a lot of conjectures, a lot of assertions, but proofs are few and far between, even now. So let me go back to the beginning. When we had the Weierstrass cubic form for elliptic curves, let's take the case where G2 is minus 12 and G3 is 0. I take this example because it's easy to draw in class for students. And you can easily see that where y is 0 is where x is plus or minus square root 3, as well as x being 0. So you can draw the curve f equals 0 easily. But now if I reintroduce the parameter g3 in this problem, in this curve, then what I'm going to see are a family of curves, which as G3 varies, will change the roots on the horizontal axis until those roots coincide, and that happens when G3 is plus or minus 8 for this example. And then you can keep going. And then beyond that point, for other values of G3, you're going to get other curves in this diagram where you don't see where you only see one real root. But in any case, it's easy to see that what you have is a one-parameter family of curves, and these families are called pencils. And so here's another version of such a picture where I've fixed G2, not necessarily equal to minus 12, as in the previous slide, but now I'm allowing G3 to vary. And so remember that each time, so I've fixed G2 in this picture, I'm allowing G3 to vary, and each time I pick a value of G3, I pick a curve, or a component of a curve on this diagram, and a point on that curve is parameterized by this Weierstrass P function and its derivative, because of the differential equations I showed you earlier. So to follow the dynamics means I'm following points on such a curve, and each time t is shifting, I'm just moving along the curve. So this just is a real slice of the picture, which is really too complex dimensional. Now, if I'm thinking of it this way, then where could this picture go wrong? It goes wrong when the curves coincide. They don't coincide in the finite real picture you see here, but they do coincide, they do intersect at infinity. And, well, you might say I don't care about infinity, but actually infinity is where the solutions of the Weierstrass differential equation have poles. So you do encounter them in real life, and for finite values of t. So you do need to know something about how to get through that complicated region. And because they all intersect at infinity, we now have to look at these curves in projective space. It depends on your favorite projective space, which one you choose. Here is just a snapshot of CP2, complex projective space of dimension 2. And I like to work with affine coordinates because it makes it easier for me to get explicit information. So there are 3 charts covering CP2. And to work at infinity, I'm looking at, for example, where y goes to infinity. Remember, y is the derivative of the p function, and where x is infinite, so will y be. They both have poles at the same place. And that's called a base point of the pencil. They all intersect there. And so I'm also interested in the line on the right-hand edge of this triangular chart picture, and I'm going to label that as L infinity. And so we had this problem at the base point, where all the curves go through the point. And so in order to resolve the dynamics, what I need to do is to ask if I'm following one of the curves, that's like following a line in this picture here, where they intersect is the point at infinity that I drew on the previous slide. And so the question is, how can I continue the solution through that point? And the way to do it is, of course, resolution of singularities or blowing up. And this is a nice picture from Dijkstermat's book on QRT maps. Basically, you take each line and you pull it up onto this new line that replaces the problematic point. And by doing so, what we do is to allow ourselves to continue the dynamics of each solution through a pole of the original p function. Okay, so if I keep doing this, it turns out, as many of you know, in CP2 you have to blow up 9 times to resolve that cubic pencil. and you get a schematic diagram of lines that you introduce along the way each time you blow up a point. So the original line at infinity is drawn in blue here, and each time you blow up, you are potentially creating new exceptional lines, as it's called, and on each such exceptional line, there might be another point, and so on, and you keep going, and you get a diagram like this. This is called the intersection diagram. And after 9 blow-ups, everything's done. There are no more singularities. Everything is well defined. The dynamics are beautifully separated. So what does that mean? Well, this picture is actually, as I think other people have mentioned, mappable to, it's either called the Duval correspondence, the Mackay correspondence, or Coble correspondence, somebody tell me, to a picture where each such line is replaced by a vertex, and you create an edge between 2 vertices if the lines intersect on this diagram. And when you do that, what you get is the Dinkin diagram of the exceptional Lie group E8, extended E8. So the elliptic pencil that we started with has a resolution which corresponds to the E8 group, Afan-Weyl group, and in a sense that characterizes the dynamics of what's happening on each curve of that elliptic pencil. I want to show you another system that has the same intersection diagram. So this is a system we studied, myself with Dijksterman, some time ago. The paper appeared posthumously because unfortunately Dijksterman passed away in 2010. But we looked at a system, and I'll tell you in a minute where it came from. We wanted to study it in an asymptotic limit, that is where t is becoming infinite, unbounded. And if you look at the system, it's actually a Hamiltonian system, where the Hamiltonian is called E for historical reasons. And in fact, that E, if you considered it as a parameter, gives you the Weierstrass pencil. It is exactly the same as the Weierstrass pencil if you take G2 to be 2 and G3 to be, I think it's 2E. So, but it's a very different system of differential equations. In particular, note that the right-hand side is not autonomous. If I had the Weierstrass differential equation, I wouldn't have the last term on the right of both equations. I would have it without those extra terms, and you would go back to the Weierstrass's differential equation. But this is what we have, and this is a Hamiltonian system. But this picture is not the same because the E, the Hamiltonian, is not preserved because of those extra terms in the system. And it's not preserved because if I take the derivative of this equation, which looks like Weierstrass's equation, I get a term which doesn't vanish on the right-hand side. As t goes to infinity, it goes to 0. But unless I'm at that limit, I don't have something that, that corresponds to elliptic functions. And in fact, what I have here is a version of the first Painlevé equation. It's exactly the first Painlevé equation, but in a different system of coordinates that was actually given by Painlevé's student Boutroux 100 years ago, more than 100 years ago now. And we've just formulated it in a different way. And so what we see here is 2 things. One is that in the limit t goes to infinity, the solutions of this system approach elliptic functions. Secondly, it shows us something is different about the geometry. the geometry that I just spoke of with resolution of singularities. What is the difference? The difference is very simple. It's in the last base point that we blow up. That base point now varies with t instead of being fixed by the system. In other words, I still have an exceptional Lie group of rank 8, affine Lie group. I still have the same blow-up structure, but the last point changes in time. In other words, the pencil, where they all intersect, moves as you change time. And so we get a picture which is very different, where the elliptic functions or elliptic curves would have lain on one slice of this picture. What we get is each time we change t, we're shifting to a new slice and a new slice. And so we have a family which is fibered by a Weierstrass pencil, but the pencil changes as you change t. And this is what Okamoto described in 1979 when he was talking about the initial value space of the Painlevé equations. He had this kind of geometric picture in mind. What we've done is to look at it in the limit as t goes to infinity. And this is actually one of the greatest things that Okamoto did. He was visiting Strasbourg. He was inspired by the French algebraic geometric school. And so he created this theory. But his favorite projective space was a bit different. He worked in the Herzebruck setting in F1. And there you have 4 charts, which is useful for other contexts. So here in this system, instead of the 3 charts that I showed you earlier, we have 4 with slightly different choices of affine coordinates. It's not hard to work in, but you have to remember that the self-intersection numbers of certain lines are different. And in this setting, if you were to, for example, take that line at infinity, which was drawn in blue, the horizontal line at the top of the chart diagram, and consider 4 places where you're resolving your dynamics, what you find is that if you take a case where you have 2 more blow-ups on each line, there is a system that has this structure, which is the 6th Painlevé equation. And the 6th Painlevé equation has also a movable base point. The movable one I've indicated here, it varies with the independent variable in the equation. And I've just drawn it schematically with that red point. So in other words, as t changes, that base point changes, and so the line is tracking back and forth on this line at infinity. So there's a very beautiful geometric picture underlying all of the Painlevé equations. And that geometric picture is almost exactly like elliptic curve theory and the algebra geometric description of elliptic pencils. The only small change is that some of the base points may change with time in your system. And so that's why I call my talk Dynamics on and off elliptic curves. When you're in the Painlevé setting, you're actually going from one elliptic curve to another as time changes. Whereas in the elliptic curve setting, the original setting, you're following just one curve in the original pencil. So in this case, what we have is the Dinkin diagram of affine D4. Yes? Of course. Yes, it's related, yes. But I'm going to come back to that picture. It's not quite the same, but there's a dual picture with the 4 points as well. I'll come back. I'm almost there, actually. And just to reiterate, that picture that I just showed you corresponds to another Hamiltonian system with a Hamiltonian or E given by this non-autonomous curve. And that was the end of a long story that I was following since my work with Dijkstermaat, and I worked with Victoria Hoyer at Strasbourg on this last paper, and because this is the Painlevé 6 picture. So in all of that theory, what we were able to show was that if you're looking at Okamoto space in an asymptotic limit, you can show the existence of a repeller set in that space. That repeller set is effectively the union of all of those divisors in the pictures that I showed you. This allows you to create an kind of a topological argument to show that the number of poles and zeros in the transcendental solutions must be unbounded, and that there is a complex limit set for each solution. These are things that may have been suspected before but never ever proved. So that's one half of the story. This allows us to create or describe some global properties of the dynamics that had not been proved or shown before. But this is not everything. Because in addition to the differential Painlevé equations, there are discrete Painlevé equations. The same way you have, say, a difference equation for elliptic functions, which comes from its addition formula. So the addition formula is a birational map of points on a curve, elliptic curve, and you could consider that as a discrete dynamical system by iterating addition on each curve. There are also counterparts like this for the Painlevé equations. There are discrete equations, discrete dynamical systems. What can we say about their solutions, which are also regarded as new transcendental functions? And this is not just an abstract question, because these discrete Painlevé equations are now known to arise in tiling problems. Aztec tiling problems, for example, give rise to equations that are given by, that map to the discrete Painlevé setting. So in order to explain the context, I need to explain that there is a very strong geometric school in Japan that has grown under the influence of Okamoto and many others. In particular, Sakai at the University of Tokyo created a way of describing all of the known discrete and continuous Painlevé equations through the intersection diagrams and their corresponding affine-Weyl groups. And this is his diagram, slightly corrected by Rains. And in this diagram, what you see is a structure which gives you E8 at the end. That corresponds to the first Painlevé equation. And way on the top left is the most general equation. That's an elliptic difference equation. And along the way, so let me just show you, this bottom right corner is what Okamoto described. These are where the differential equations sit. But along the middle line are where there are Q difference equations. And I'll just go through very briefly a couple of examples from that green band. I won't be able to go to the elliptic case at all because we know nothing. We know nothing about the elliptic difference case, almost nothing. So I'll just briefly mention two cases which correspond to A3 and A5 in this diagram. They're sometimes called Q Painlevé 6 and Q Painlevé 4, but the name doesn't quite matter here. So in order to describe what I was saying for differential case, but now for discrete case, we need more tools. More ways of describing, deducing their global behaviors. So I went to look at the dual story behind the Painlevé. And this is where we come back to connections and moduli spaces. The dual story is that behind every Painlevé equation, there is a linear system. And the linear system, represented here as a matrix linear differential equation, has singularities. The coefficient matrix A has a singularity, say, for example, at Z0. And you know this from elementary differential equations theory, that if you allow yourself to move on a path that encloses such a singularity, the equation doesn't change, but the solution you started with may undergo a transformation. And that transformation is captured by multiplication by a constant matrix, which is called the monodromy matrix. So the model problem of the hypergeometric equation is that we have three singularities. They are Fuchsian singularities at 0, 1, and infinity. There's the differential equation. And we know that each time you go around one such singularity, you're going to get a group transformation, and basically you create a monodromy group, or if you like, mapping class group, or character varieties, by considering these changes in representation theory. So we have monodromy matrices which come from going around each point. There's relations between them due to the fact that we're looking at solutions of the same equation. It's fascinating that the story of this goes back not just to Lazarus Fuchs, but to his son, Richard Fuchs. So this is Richard on the right. And I believe Lazarus gave him a problem to work on, because Lazarus was so famous for hypergeometric equations, which has three singularities, remember? He told his son to work on the case where you have a fourth singularity. What happens then? So that's what he did. So he looked at not just 0, 1, and infinity, but a fourth point, which you can't map to anything else. So he called it T, let's say. And he asked, what is the condition on these coefficient matrices such that this monodromy data that I spoke of, coming from the monodromy matrices and their traces and determinants, stay invariant when I move T? And if you do that, you get the sixth Painlevé equation. That appears as the underlying equation that relates the coefficient matrices. And many people have said this before, it should really be called Richard Fuchs's equation, because he discovered it first in 1905. And then Painlevé and Gambier brought it in under their umbrella. It's another fascinating connection with Klein, that if you looked at the traces of products, pairwise products of the monodromy matrices, call them X, Y, and Z, then they satisfy a cubic relation. This cubic relation has coefficients which come from traces of various kinds related to these matrices. And this actually appears in the books of Klein and Fricker, which I think Christoph referred back to, the icosahedron, the study of the icosahedron and so on. And this beautiful equation pops up again in Jimbo's work, where he studied the monodromy problem associated with the sixth Painlevé equation. And this equation, which has 4 free parameters, which is the most general you can have in this class, if you take certain limits of various kinds, lead to other cubics, which correspond to monodromy surfaces for the other Painlevé equations. So there is another beautiful theory, geometric theory, underlying this connection. But the reason I want to explain this to you is that this surface theory also corresponds to dynamics. Why? Well, let's take the cubic surface for Painlevé 1. That's the simplest one. There's the cubic equation. It has no parameters, because the equation has no parameters, the differential equation. It has 5 lines, 5 affine lines, they're written here. You can easily check that they satisfy the equation. And they all lie on this surface. But each time you look at one of those lines, they correspond to a special solution of the Painlevé equation. So for example, if I chose L4, they all intersect. That's why I've drawn this pentagonal diagram to show the intersections between them. If I take the case L4, that corresponds to a certain asymptotic behavior of Painlevé 1, which is called a truncated solution. This is just a numerical picture of the poles of that equation. And there's truncated and then there's tri-truncated. They arise as important solutions in mathematical physics. This is tri-truncated, the one that corresponds to the intersection of L1 and L4. There are also things called symmetric solutions. They correspond to special points on the surface. They're called symmetric because if you look at the infinite number of poles in this transcendental solution, they are arranged in 5 sectors, and each sector is a discrete rotation of the other. In general, it's not, but this special solution has that property, that it's invariant under discrete rotation by 2 pi on 5 in the complex T-plane. Okay, so this is just a very simple, small insight into how monodromy surfaces are related to solutions, and we decided to look at whether such a thing could happen for difference Painlevé equations. And we had some small steps that I want to briefly mention to you. Instead of singularities in differential equations theory, there are singularities in the sense of where the coefficient matrix vanishes in the difference theory. In the difference theory, this is one case of QP4 or QP6. And this is the picture corresponding to QP4. The x's here are where the determinant vanishes, the determinant of the coefficient of the linear difference equation. You can define sectionally analytic functions inside and outside that line which isolates those 6 points from its iterates. You can define a connection between the outside and the inside solutions. The connection matrix is called C here. You can also characterize the asymptotics to fix things of the linear solution. And these singularities of that connection matrix give rise to monodromy manifolds. So the counterpart to the continuous differential setting is another expression which corresponds to monodromy in a difference equation setting. And this is what it looks like for that case. This is the monodromy surface. It's also cubic. The coordinates here are P1, P2, and P3, but there are coefficients given by theta functions. And it's fascinating to ask, how do the special points or special lines on this surface correspond to solutions of the nonlinear difference Painlevé equation? And we did manage to make a tiny bit of progress. I won't go through the QP6 case, but there are symmetric solutions you can identify from such surfaces that had not been known before. So this is a symmetric solution of QP4, symmetric because there's this relation between Q multiples of the iterate. There are certain initial values that correspond to those symmetric solutions. There are 4 such solutions, and you can show that the corresponding Riemann-Hilbert problem is explicitly solvable. There's a very rich structure here that has barely begun to be considered. There are many, many open questions, and one of the other elements or directions we're trying to pursue is whether there is an arithmetic version of this construction for the Painlevé setting. like there is for elliptic functions. But as I say, there are many open questions. What are the global behaviors of the new functions? New in the sense that they're more higher transcendental, but now solving difference equations. What are the monodromy manifolds of other discrete Painlevé equations? I've only shown you 2 cases, but those are the only 2 that are known. What information can we deduce from these monodromy surfaces? As I showed you, the coefficients are theta functions. They depend on multiple variables or parameters. So they are actually families of surfaces in a different sense to the ones for the differential case. We don't know how that's giving us more information. And what do we do about elliptic difference equations? That's completely open. And I think I'll stop there. Thank you very much.